Good morning, all. Today we are going to study the how to draw the layouts of different CMOS combinational circuits using Microwind software. So basically, first we will see how to correlate with your logic diagram and its respective layout. Okay, so how to draw the layouts for different CMOS combinational circuits. Okay, and then we are going to simulate it using the Microwind software. Whether the screen is visible to you? Yes, whether screen is visible. Whether screen is visible. आहे का नहीं है कोणी?
Yes, ma'am, it's visible.
Okay, fine. So first we will see how we will start with the CMOS inverter first. After the CMOS inverter, first we will see how is the CMOS design of this inverter, and then we will draw its layout, and then we will simulate it in the Microwind software. Okay, so first we will draw the inverter circuit, or simply in a NOT gate. Okay. So how to draw the CMOS inverter circuit first? That we have already studied. We have seen its VI characteristics too. So first, what we have to do, the logic diagram of the CMOS inverter. CMOS inverter means this consists of the two sections. One is the pull-up section, and second one is the pull-down section, right? So in pull-up section, it has the PMOS transistor. PMOS transistor means there is a bubble on the gate side. Okay. And pull down section consists of the one NMOS transistor. The gate of both the transistor is connected together, and that will be nothing but your input of a NOT gate. Okay, so this is simply an A, which is an input. Okay, and whatever is the pull-up section, the source of the pull-up section is always connected to the VDD. VDD, it is the positive voltage, and the source of the pull down section is always connected to the VSS, that is the ground. And if this is your source, this is your gate, then the next terminal will be your drain. Fine. In the same way, if this one is the source, this is your gate terminal, then this next terminal will be the drain, and this common drain point, it is nothing but your output Y. Okay, where you are getting the inverted output, inverted input. Y is equals to A bar. So this is a logic diagram, CMOS combinational design of an inverter circuit. Okay, in case of your symbol, how we represent this NOT gate, this is our NOT gate, where A is the input and Y is the output, where Y is equals to A bar. So this is one of the representation of, or the inside view of your this NOT gate. But again, we have seen, we have drawn this in terms of a different transistors. Okay, but how these transistors are typically formed? Those are formed with the help of a different layers of the P-type and N-type semiconductors. Okay, so if this is your PMOS and this is your NMOS, right? So we have seen its construction also. For NMOS, we use the P substrate on which there are two diffusion layers are there. So next, once you have a CMOS combinational design with you, the next step is to initially we will draw its stick diagram. Okay. So the very simplest way of drawing the stick diagram, just stick diagram is the rough sketch of your layout. Okay, rough sketch of the layout. It is showing you simply the means all the layers, all the diffusions are shown with the help of a single line. There will be no any thickness or thickness for that particular line. There will be no any length and breadth. Okay, so simply each diffusion we are going to show with the help of the respective lines only. So in case of your PMOS or the NMOS, how these transistors are represented? Okay, so for NMOS, the transistor, or NMOS or the PMOS, both the transistors are represented in the same way only. Okay, so we have seen its structure, right? Structure means construction. The cross section, and that construction, it is actually a cross section of that particular transistor. So for NMOS, there is a P substrate is there, and on which there are two N plus diffusions are there, and in between that there is a gate terminal, right? So again, if you see its 3D view, then this one is the middle one is your gate, and on the both the sides of the gate there are the source and the drain. Okay, source and the drain. So here, if depending upon the polarities applied, you can consider it as either source or drain. You apply the positive VGS between the gate and source, and the drain and source, again you apply the positive VDS. So positive terminal will be connected to drain and the negative terminal will be connected to the source. Okay, so this is the construction of your NMOS, N plus diffusion. So if you just see from the top, if you see the top view of this, there are in middle will be the gate region, on opposite side of that gate, one terminal is the source and another terminal is the drain, and this is your diffusion layer. So simply your NMOS will be represented, if this is your N diffusion, okay, this is your diffusion area, and if your poly cuts the diffusion, then it forms a transistor. Then this is suppose your polysilicon gate. Okay, so this forms a transistor. So this is your polysilicon gate terminal. So on one side of the gate, the terminal is a source, and another side there is a terminal which is a drain. Okay, so this is for the NMOS. In the PMOS, same. Now this line will be represented by the P diffusion. So there are various color codings are actually used. P diffusion is there, and again whenever poly cuts a diffusion, it forms a transistor. So this is my P transistor, and this is a PMOS and the NMOS. Again I am showing this is a source and this one is the drain. Okay, you can interchange these symbols also depending upon the interconnections. If your number of transistors will get increased. Okay, now in this case, for N diffusion or NMOS, you need a P substrate. Okay, and for PMOS you need the N substrate. So on a say, if you are using the same type of a base, then you need to create a well of that particular type. So there is a need of creation of the well. Right now for stick diagram we will not generally show it, but for understanding purpose we will see this as a N well. N well, it is nothing but a kind of the substrate only for that particular PMOS. Fine. Now this PMOS and NMOS are there, which are there separately. Now we have to form this inverter circuit. Okay, and we know the interconnection of this inverter circuits. What is there now? You can see the gate of the PMOS is connected to the gate of the NMOS. So there is a connection between the two gate terminals of the PMOS as well as NMOS, and to that you are applying the input A. So in the same way, this vertical line is nothing but a gate terminal, and this is another vertical line of the NMOS is a gate terminal. So what you have to do, you have to just interconnect these two. So this will form, now this is nothing but to this line you are applying the input A. Okay, now what is the remaining? You can see for this particular PMOS, the source is connected to the VDD. So for this PMOS, if it's source, you have to connect to the VDD. Okay, so this is here you will connect the VDD. In the same way, for NMOS, the source will be connected to the ground. So for this NMOS, this is your source. So here you can connect to your ground or the VSS. Okay, ground or the VSS. Fine. Now what is the remaining connection? That is your output point. Okay, which is your output point? That is the common drain point. So drain of the PMOS and drain of the NMOS will be interconnected, and that is your output point. So where is the drain? This is the drain of the PMOS, and this one is the drain of the NMOS. So what you have to do, you are just interconnecting these two, and this will be your output Y, which is nothing but a bar. Which is nothing but a bar. So this one is the layout of your PMOS, layout of your CMOS inverter. Okay, so using this, what we have to do, we have to draw its layout. So what will be the layout? Simply whatever this diagram, you have to follow it with the diffusion. So for PMOS, we know that there is an N well is there. Okay, so N well is there. In between that N well, you have to diffuse a P diffusion layer. So this will be your P diffusion layer. Okay, so that will have some W by L. On that there will be a polysilicon. Now I am showing the polysilicon gate with the vertical line. In the same way, you will have an N diffusion layer, and whenever it cuts a poly, it forms a transistor. So this is your polysilicon gate. Now we know that we have to interconnect these two together. So this is your input, right? This is your input A. Next, what you have to do to this polysilicon, to this diffusion, you need to apply a VDD. So there will be the contact you can apply. So this is your VDD. To this source terminal, you are connecting a ground. So this will be your VSS. And what about the next drain? Now this terminal, sorry, these two will be interconnected together, and we have to apply a contact there. So those cross, square and the cross are the contacts. So that means there will be the actual physical connection will be there in between those two. So this will be your output bar. Okay, so what is this? This is the layout of your this given CMOS inverter. Then what you have to do, if you apply a square pulse to this A, and if you observe this node Y, then you will get the inverted input at that point. Okay, so initially we will see this simple layout of the CMOS inverter, how to draw it in using the microwind. What are the how is the environment of the microwind, how to draw the different diffusion layers, that we will see initially. So but before moving to the microwind, you must at least know these basics of CMOS inverter, its respective stick diagram and its layout. Okay, you can go through it in detail. Next I will show you the same thing, drawing the layout in a microwind. Okay, so here whenever you open a window of the microwind, this window will appear. There is a black screen. Whether this screen is visible to you, whether this,
Yes, ma'am.
okay. So in this there is a black color is there, completely black color with a grid is shown. Right on the left, on the right hand side, you can find the palette. Okay, so this palette is having a different layers. Okay, metal 1 to metal 6, six different metal layers are there. Then contacts are there, polysilicon gate, P plus diffusion, N plus diffusion, and anyway, I will share this evaluation version with you. You can install it on your laptops, and you will be able to practice these simple layouts at home also. Because we have a license version too for this microwind, but you will not be able to simulate it at home for with that. So this evaluation version you can use you can use at a home. Okay, so now what are the different parts that are shown here? Now whatever the foundry, by default foundry you are shown here, you can find it at the bottom of this window. It is a CMOS 0.12 micrometer 6 metal. So 6 metal layers will be there. As you increase the technologies, then this length of this gate channel will get reduced, and there will be the more number of metals will be used. So what is the advantage of having the more number of metal layers? Means you can make your design as much as compact by using the different metal layers, so that though you overlap all these, there will be no any physical connection between those metals. Means if I take a metal 1, okay, this is my metal 1, I have connected the 2 points with this metal, and suppose there is a metal 2 and this is your metal 2, you are drawing across this metal 1. So actually there is no any interconnection between these two. There is no any interconnection between these two. I will show you. So you can see this view. Once we draw the layout, I will show you this cross section too. Okay. So though you are seeing, means if you see from the top, okay, you are seeing that these two are overlapping, but there is a distance between these two layers. So you can overlap as many as possible metal layers for the interconnections between the different points. Okay, so in a compact area or in a less area, you can have multiple connections using these different metal layers. Okay, so we are going to see how to draw the how to draw the simple CMOS inverter. So what is there in this palette? Okay, so you might have used the multi-sim, right, for the simulation. So there are ready-made transistors are there. Using those tools, you just make a circuit and you simulate that, right? So in the same way, what is there here? Here there are the different layers are there, and you have to apply those layers, and from that you have to prepare the layout and you have to simulate it. Okay, so initially there is the MOS generator. MOS generator means with the help of this MOS generator, whatever the right now I told you that how the NMOS is formed. In NMOS, we know that P is the substrate. So here you can see the P plus diffusion is there. Okay, but this black screen, whatever the black screen you are showing, you are seeing that it will be your substrate. Okay, that will be your substrate, and on that substrate you are diffusing the N diffusion. Okay, so I have taken this N diffusion which is shown here by the green color, right? So what I am going to draw, this is my N diffusion layer, okay, which is a green. And if the polysilicon gate I draw across this, then this is my transistor. This is the transistor, okay. So here a poly cuts a diffusion that will show you the, see, you can see here. This is the diffusion and this one is the polysilicon gate. I am showing the cross section of this. Now you can check your P substrate is there, whatever is the green color, that is your N diffusion. So one is the source and another one is the drain. In between that you are seeing the red color strip, which is your gate. And these diagrams we are seeing as the construction of the MOS transistors many times, right? So this is a cross-section view which can be seen by with the help of a front view like this, okay? And you can also see this view, okay, the 2D view. Fine. Now next, this is an NMOS transistor. If you have to draw the PMOS transistor, then what is the PMOS? For PMOS, you need the N bit, because this black screen is your N type, P type. But for the PMOS, you need the N substrate. So this N will act as an N substrate for the PMOS. And in N substrate, you are going to use the P diffusion, okay? And whenever a polysilicon gate will be present, then this will be your PMOS transistor. So these two separate PMOS are shown here. Okay, now in order to form a CMOS inverter, we need a we need a two transistors and we need to interconnect them, right? We need to interconnect them. So what we are going to do now, we are going to draw this complete design. Okay, so again, either you can use the direct layers or you can have a MOS generator here. Okay, MOS generator is there, so directly you will have a PMOS and NMOS generated directly. So now here widths are shown for this MOS generator. Width and length are shown here. In case of the lambda, you can see the width is the 10 and length is the 2. Okay, you can change here for either you need a PMOS or the NMOS. Right now it is the 10 by 2 means the 5 by 1 is taken for the NMOS. Okay, so now you can check here, change here NMOS or the PMOS, what you want. Okay, I have selected a PMOS, fine. And then here there is an option generate a device. Okay, generate device. Now I am just click on the generate device and simply put it. Okay, click on it, click on the background. Now what you are observing, the some green dot is there. Okay, what are those? Those are the N well, because this is your N substrate on which there P substrate on which the you need a N substrate for the PMOS. So this green type is the N well. Then you can find there is the brown color also. Brown color P diffusion is there. Then red one is the polysilicon, and there are the blue color and with some contacts are shown. Okay, with some contacts are shown. Those, so it is given you ready made, that to this contacts you can interconnect whatever the things you need. Fine. So now if this is a PMOS, in the same way I am generating the NMOS. Okay, NMOS, same with the same length. Now same thing, NMOS is generated. Now what is the difference here? Here there is no any N well. Why? Because this black is the your P substrate. But here you can check the diffusion is of a green type. Okay. And same two connections are shown. Now what we are going to do? We are going to interconnect these two together. Okay. NMOS. Okay. Generate device. NMOS. Okay, this is your PMOS and the NMOS. Now what we have to do? We have to interconnect. Fine. So these two different MOSes are there with their respective gate and source and drain terminals. Fine. So as per our design, what we have to do? Our gate terminal should be interconnected. So here you can check the from the palette. You can take the polysilicon layer, and just what you have to do? You have to interconnect these two. Okay. You have to interconnect these two. So now what will happen? Now this has connected the two gates of the two PMOS and the NMOS together. Okay. Then we know that to the source of the PMOS we have to connect. See, we have seen in this diagram that to the source of the PMOS you need to connect the VDD. We need to connect the VDD. So same thing we will do. Here you can check the VDD and the VSS are there. Okay. So VDD supply you can connect, take and just apply here. Then source of the NMOS. Okay, bottom part is the NMOS. You have to connect the ground. So there is the ground is there. So you can apply here ground, VSS. Fine. Then so a drain of both the transistors you have to interconnect. See, to the sources we have applied a supply voltages. Now the another terminal is the drain. So these two metal parts you have to interconnect. Now this will be the interconnection of your two drain terminals, and that is your output point. Okay, so this is a complete layout of your transistor CMOS inverter. Now in order to simulate it, what you have to do? You have to apply the input. Okay, so to apply the input, you can see here add a clock option is there in the palette. You can take it and just click on this red button. Okay, so this you can give the label as this is your A. Okay, assign the label, and the common drain point is your output point that you have to observe. Okay, the signal at that output point you have to observe. So there, to observe a node, there is a visible node is there. I like symbol is there. Okay, so take that I and click on the this common drain point. Okay, so this is your output Y. Click on assign. Now we have applied the input. We are observing the Y node, so we have to just now simulate it. So okay, run simulation, polarize the anvil to video. Now you can check here. What is there? A, which is shown with the help of a green color, and Y, which is shown with the red color. And this is the clock. Where there is a positive cycle, you are finding the negative cycle for the output. For negative cycle, you are finding the positive cycle at the output. So what is this? I will reduce this. You can check now. More spacing is there. Okay, this is your green color input and red color is output. So simply we know that it is an inverter, so you can find the similar means exactly opposite or the complementary signal at the output. Okay, now one more thing is there. You can check here 6 picosecond and some 7 picosecond, some values are shown. What are those values? Those values are of the rise time and the fall times, right? Rise time and the fall time of your signal. Now right now we have not connected any load here. Okay, we have not connected any load here. Okay, so this is your simple circuit, simple CMOS inverter with, now here we have not changed any W by L ratio also. So just for initially understand how to draw the different layers, these things you can also draw with the help of the separate layers also, but there is a MOS generator present in between in bit, so you can make a use of that for drawing the each of PMOS transistor. Okay, so same thing we will first check for the NMOS inverter too, sorry, not gate and the NAND gate. Let's see if we have seen a NAND gate. I will directly draw go to that particular diagram. Okay, NAND gate is there. See, now here again a NAND gate is there. How to draw the layout of this NAND gate? Fine. So for this NAND gate, initially you must be able to draw the stick diagram. Stick diagram is a rough sketch. Once you have it with you, then it's easy to understand which 2 points we have to interconnect. Okay, so for this NAND gate, we can see that the two PMOS are in parallel and two NMOS are in a series. Okay, so initially we can just we can give the names to the different terminals. Okay, so if this is your VDD, okay, VDD of the pull-up section or the source of the pull-up section is always connected to VDD. So this is your source, this one is your source. Okay, for this PMOS transistor, this is your gate. Okay, and if this is source gate, then this will be definitely a drain, right? If this is source, this one is the gate, then this third terminal will be the drain. And this drain and this drain both are connected together, and that will be your output Y point. In the same way, the source of the pull down section is connected to VSS or the ground. So if this is source, this is we know that this one is the gate, and this one will be your drain. Okay. Next, if they are in series, means drain source, drain source. So if it's, and this we know that this is a common drain point. So for this is a drain. This one is the gate, and this one will be your source. Okay, because they are connected in a series. So drain source, drain source. Now we have labeled all the terminals of this NAND gate. Now we have to draw the stick diagram. Okay, now we have to draw the stick diagram. Now here you can see the two PMOS and two NMOS are there. Okay, and whatever the PMOS or the NMOS circuits are there, all will be fabricated using the same diffusion. All are fabricated using the same diffusion layers. That's why if this is my one transistor, okay, then these will show you the two transistors. Okay, this will show you the two transistors. So diffusion layer is common. They will be differentiated with the help of this gate and whatever the interconnection we want for these in between these gates. Okay, so for this, how to draw the circuit? Okay, how to draw the stick diagram? Let's see the p diffusion first. Okay, if this is my p diffusion, okay, two transistors are required, so these will be the two polysilicon gates will be there. One is a A input and second one will be the B input gate. Okay, in the same way for NMOS, same thing will be there. This will be the one gate and one transistor. This is another transistor, and we know that the gate of both the transistors should be interconnected. So these are your A and B inputs. Now we have to make the different connections. Now for pull-up section, the source of both the transistors are connected together and we are applying the VDD there, right? Source is connected together and we are applying the VDD. So you can either make this as a source, okay? You can make this as a source. Suppose this is my drain, okay? This is source, then this is source and this one is drain. So this is my common source point and this here you are going to apply the VDD. Drain, source, source, drain. See, you can check, you can simply trace in this way: drain, then source, and then drain, right? Drain, source, and then drain. So these are the four different terminals you are scanning. Okay, so in the same way for A, first we are seeing this A transistor. So next thing, to this again A, we know the gate is the common terminal. Fine. So this is your drain, source, right? Drain, source. This will show you the series connection. So if this is your drain, source, drain, and source. Okay. Source and drain, they are interconnected together. Okay. And source of the B is connected to ground. So this will be connected to the ground or the VSS, right? This is connected to the VDD and this will be connected to the VSS. Input will be applied to these gate terminal. One clock signal will be given to this gate. Second clock signal will be given to the another gate. Okay. Now, where is the output point? Where is the output point? Output is connected between the common drain point of A and B PMOS. Common drain point means this is, right? This is your PMOS and this is the drain of the NMOS, right? So here there is a connection, here there is the connection. So we are interconnecting the two drain points and third drain is of A. So this is your third connection. Okay. So this is your common output Y, which is the simply NANDing of A and B. Okay, see, this one is the connection, which is your output connection. So for that, you can use the metal layer. See, apart from the basic diffusion layers, if you are going to interconnect the two, then what you can do, you can simply take the help of the metal layers to make those connections. Okay, so this is a stick diagram of your NAND gate, and same with the help of the same diffusion, what you have to do, you can draw those NAND gates too. Okay, how to check the same thing now for this Microwind? We will take a new. Fine. Now here you can check again a palette. MOS generator. Okay, MOS generator. Same thing is there. PMOS we are generating. Now here we needed two PMOS transistors. Okay, so those will be fabricated on the same substrate. So here number of fingers is there. Okay, here if you specify by default one, so there will be only one transistor is there. But now we have a two transistors. So here take a number of fingers as a 2 and click here. So now what is there? You can see the two transistors are there. The two polysilicon, two red lines means two transistors are there. Okay. So in the same way, what you can do, you can generate the NMOS too with the two fingers. Okay. CMOS. Okay, now here what we have to do, we have to interconnect these two. Okay, we have to interconnect the two polysilicon gates. So what you can do, you can go here and make the connection between these two. Fine. So you can make a two gate connections. Then we have seen the to the common source point you are applying the VDD. Okay, so this is the common source point. This is you can apply the VDD. Ground you are connecting to the common source point, right? Here it is the common source point. We are connect a common not last source of the B. Here you can apply in the VSS. Now inputs will be given to, this is the clock 1. Here you are applying A. Okay, here applying the A assign, then second input B. Now somewhat slower clock we will apply. Okay, otherwise both the clocks will be same. A B. Now output point, which one is the output point? See, this is your output point. You can interconnect these two metal one layers together. These two layers you can interconnect, which is connecting. See, either you can connect it from upper side or the lower side too. And this one is your another drain. This one is your another drain. Fine. And here you, that point you can connect as your output 1. Output 1 assign. Now you can check here, it is an AND gate. When both are 0, then only your output will be, if both are 1 and 1, then only your output will be 0. For all the cases, your output will be 1. Okay, so you can check here. In this case, both the inputs are 1. This one is a green. A is shown in the green, B is shown in the white, and output is shown in the red color. So here both are the 1. So your output is 0 in that period. For remaining time, your outputs are, for all the other combination, your output is 1. Okay, so this is your NAND gate. So in the same way, for any of the given circuit, given combinational design, you can draw its stick diagram, and according to stick diagram, from the stick diagram you can understand which different parts you have to interconnect, and then you can simulate it simply applying a different clock signals to its respective polysilicon gate, and by observing the output, which is the common drain point of the pull up section and the pull down section. Okay, once you practice it, hardly it will take a 5 to 10 minutes, maximum 5 to 10 minutes to complete each practical. Okay, so as a part of the experiment, performing the experiment, it will ask you to draw the NAND and simulate it. Okay, so it is expected to draw the CMOS combinational design, its respective stick diagram and the layout. Fine. Again, the very important thing is, now we have drawn here a different layout, so I can take a length or the width for these layers. Okay, so what should be the distance or spacing between the diffusions? It has rules. Okay, those rules you can define whether this circuit is violating the rules or not. It has a DRC, design rule checker is there. Okay, if you click on it, and if there is some error, means the spacing should between these two, it is a less than the given rule, then it will show you the error there. So for right now, for this circuit, there is no any error you can find. Okay, so this is the after completing the design, you can just click on this DRC, so to check whether your design is violating any rules or not. Okay, so you can make a practice of this drawing the layouts. Again, we will utilize one more hour in the next session to draw the further designs, and also to understand how to decide that sequence, which one will be the source, which one will be the drain in more detail. So that well, means once if you have a 3, 4, 5 up to 6 transistor in your combinational design equation, then for that how will be the sequence: source, drain, drain, source, source, drain. So you have to follow some path for that, and same path should be followed for the pull down section also. So based on that, you can have a, you have to keep in mind that you have to reduce the connections as much as possible by taking the proper sequence for those transistors. Okay, and sometimes you need some external connections to. Right now we needed this connections of the metal to connect the two drains. Okay, so that you have to just keep in mind. At this stage there will be very smaller circuit you have for the layout. Okay, once you understand, then we have to draw the layouts of the full adder for the sum and the carry. So what is the equation of sum and carry? You will draw its combinational design and then its particular layout. Okay, so this is a simple circuit of having a 2 transistors only. Okay, so again in the next lecture we will revise this part. Again we will see how to select the sequence of those source, drain, drain, source for the respective transistor. Okay, we will stop here.